Hi all, thank you for tuning into my channel, a channel on ozone technology course. This session is session 9B and we'll be having a discussion on the two types of biocides. One is the oxidative biocides and the other one will be the non-oxidative biocides, and we shall be discussing the effects of each of the biocides on a cell. The oxidative biocides are generally oxidizing chemicals such as chlorine, iodine, and bromine. These are the chemicals that dissociate to halogens such as in bleach, sodium hypochlorite or calcium hypochlorite, that is a solid bleach, peroxide, which is hydrogen water with an additional oxygen, and finally ozone, which is a triatomic oxygen. The effects of these chemicals are time and concentration related. In other words, the higher the concentration, the shorter the time. But bacteria will not develop resistance to these chemicals simply because these chemicals carry out oxidation, or in other words burning of the cell, and the application is strictly limited to safe concentrations without harming animals or humans. Fluorine, chlorine, bromine, and iodine are called halogens. They all act in the same manner. The rate of reaction decreases in the order from fluorine to iodine, with fluorine the most active and the iodine the least active. Unfortunately, fluorine is so very active that it is virtually difficult to control the reactions and therefore unsuitable for normal applications. Bromine itself is toxic and is less acceptable in use, but can be used in very low concentrations, which will not be in the toxic range. One important property of bromine is if the bromine is dissolved in the water, it can handle at higher temperatures and the bromine does not break up. Iodine is the least reactive but still effective as topical antiseptics. In other words, iodine is kept on wounds for a long period of time with less concentration or less effective oxidation biocide. Chlorine, therefore, is the most favorable biocide and commonly used in most oxidative biocide applications. One thing I did not mention to you is that iodine is the least soluble in water compared to all the halogens, and because of that it is more difficult to use it effectively. Now, we have discussed earlier the mechanism of formation of the oxygen radical when OCl breaks down to chlorine and oxygen ion. Now, when chlorine is dissolved in water, it forms HClOs. When sodium hypochlorite is dissolved in water, it breaks down to sodium positive and OCl negative. Now, the active oxygen radicals that react with carbon double and triple bonds and also oxidize the protein in oxidizable components in the same way as ozone would. The strength of the chemicals are chlorine dioxide, chlorine, and OCl, hypochlorites. The disadvantage this oxygen atom against ozone is that the rate of reactions is very slow because the oxygen radical from the chlorine has less energy than the oxygen radical from ozone. In other words, ozone acts extremely fast comparatively and more aggressively than the halogens, so that the oxidation or oxidative reactions take place very rapidly. We will be showing this in the later slides. The cell can be destroyed by oxidation of the cell membrane. Chlorine will eventually destroy the cell membranes and oxidize its contents, but very slowly, and eventually the cell dies. Ozone, on the other hand, kills the cells in two ways. The first, because of this high oxidative capacity or high redox potential compared to chlorine, it has got a higher potential than the potential difference between the cell walls, and it causes the cell membrane to rupture, further increasing the outer cell potential and disturb the electropotential balance of the cell will also lead to the instantaneous death of the cell, after which the membrane ruptures. So you will notice that ozone acts on the cell in two ways. Chlorine would act in two ways, but it will be extremely slow, and unless you increase the concentration to very high levels, these reactions will not happen. And further, you cannot use chlorine at very high concentrations simply because after the chlorine has been used, sodium remains and it builds up. Ozone gas can destroy singularly exposed cells. It also specifically destroys the epithelial cells of the lung, and therefore ozone is toxic to the lung. Ozone will not destroy ordinary cells which are multicellular. However, if it is single cellular, it will also break down weak and aged cells that are normally also broken down in the body, and those cells are dislocated from the multicellular layers of the organ. The mechanism of destruction of the cell by ozone is, first, it disturbs the voltage balance, which is 80 millivolt. That is the current voltage, and the ozone has got a 1.7 volts, that is 1700 millivolts, and therefore such a high voltage will immediately create some sort of electrical shock to the membrane and disturbs the balance, and the cell dies because it can't continue with the sodium pump. Once the cell is dead, the cell breaks down. The ozone also reacts with the protein layer of the cell membrane, the phospholipid layer, and it reacts with the conjugate bonds and will cause the cell wall to lyse. The cellular contents of the cell wall then is just distributed in the liquids, and ozone will start oxidizing them, or normally creates a flocculation and puts them into a precipitate. In multicellular organisms, ozone will have less effect as only the weak cells are killed and there is insufficient ozone to kill all the cells. So ozone is pretty safe for animals, birds and humans. And in medical science, ozone has been infused very gradually in the arterial blood so as to distribute the ozone equally and solve many diseases. I want to emphasize again that ozone causes the destruction of single cells but has very little effect on multicellular tissues, as again it will destroy weak cells, weakened aged cells, but the organs, tissues, etc. will not be destroyed or even affected. Soluble ozone, that is ozone in solution of water, has got beneficial effect on humans and animals and is increasingly used in medical therapy. Please also understand, when it comes to the toxicity of ozone to the lungs, it is clearly time and concentration related. So you have to have a reasonably high concentration of ozone for a long period of time of exposure for the lungs to be irreversibly damaged. This slide gives you the difference between ozone and chlorine with respect to the bacteria survival rate or kill rate. We normally measure inactivation or activation of bacteria using E. coli as a desired bacteria, simply because firstly it is very easy to handle and it is very reliable when we do tests. If you look at the chart in the left hand, you will notice the relationship, the charts that show the relationship between the concentration of free chlorine and time and the death or survival rate of the bacteria. So at 18 ppm, you will see that the most of the bacteria gets killed within 1-2 minutes. At 10 ppm or 9 ppm, you will have approximately 1000, above 1000 bacteria survival in 10 minutes at a concentration of 0.8 ppm. You will have almost also just slightly below 1000 survival, and when the concentration is zero point 0.2, you find that you need 30 minutes to ensure the full kill. But chlorine doesn't kill all the bacteria. There will be always some bacteria which are quite resistant and survive. And if you really want to kill all the bacteria, you have to ensure that you have a very high chlorine level. Now, the line on the red simply shows a decay of chlorine with respect to time. That is, it decays from 15 ppm to about 12 ppm in 30 minutes. Now, the chart on the right shows you the inactivation of bacteria by chlorine on 3 different types of bacteria of Citrobacter. You find that the weakest bacteria and is affected by chlorine is Citrobacter species yellow, I call it SAMRC10. You find that when the free chlorine is 0.75 ppm, almost all the bacteria are killed, and at about 1 ppm, both Citrobacter, some RC10 and some RC8 are killed, but as the concentration goes higher, you notice that the bacteria is able to survive better. What this chart shows is the effect of chlorine is not necessarily complete. It does not kill all the bacteria, and therefore some bacteria may be able to survive and carries on after the treatment. This slide gives you the rate of kill of bacteria killed by ozone. This shows different types of bacteria. The concentration of ozone applied is less than or about 0.02 ppm, and you will find that at that concentration, all the bacteria, Aspergillus, Brettanomyces, Campylobacter, Listeria, Pseudomonas, Salmonella, Staphylococcus, and Trichophyton, are killed. It says 99.99%. Please understand, when we term 99.99 or 999%, we always assume there is one bacterium survival, because it's very difficult to measure total kill. And so because 100% is perfect. The chart in this slide gives the relative kill rate of bacteria between three chlorine compounds and ozone. When I talk about kill rate, it can also be called an inactivation. You find that the three chlorine compounds include chlorine, chloramine, and chlorine dioxide. Why chloramine is put in is because when in a swimming pool, for example, when you add chlorine and lots of people swim, they have body fluids, body liquids, oils, perfumes, skin lotions, etc. They all tend to get mixed with the water, and chlorine reacts with that water with those compounds to form chloramines. So chloramines are part of the swimming pool water when it is being treated with chlorine. That is why chloramine is included here. So if you compare the inactivation between the three chlorine compounds and ozone, you will be able to understand which is the most effective biocide. First, you will notice that the standard value is called a CT value, which is concentration time, milligrams per minute per liter. So all the units given here are milligrams per minute per liter. Now on the top you have 0.5 log, 1 log, 1.5 log, 2 log, etc. And each log, instead of giving units, they express it in log forms, because 0.5 log, the difference between 0.5 log and 1 log is 10 times. And between 1 log and 1.5 log is 1.5 times, that is 15 times. And between 1 log and 2 log is 100 times, etc. So if we look at 0.45 log inactivation, you find that if it is chlorine, you need 17 milligrams per liter, per minute per liter. Chloramine, 310 milligrams per minute per liter. And CT value of chlorine dioxide is 4, and for ozone is only 0.23. So you find the least effective is chloramine, most effective is ozone, and next effective is 4, and chlorine is more effective than chloramine, but less effective than the other two. So likewise, you find that for 1 log inactivation, 35 chlorine, 615 chloramines, 7.7 chlorine dioxide, and 0.48 ozone. For 1.5 log, which kill will be 52, 930, 12, and 0.72. And for 2 log, 69, 1220, or 230, 15, and 0.95. At 2.5 log, you need 87 milligrams per minute per liter. In other words, 87 milligrams per liter per minute. And for 3 log, 104 milligrams per liter per minute. Ozone, it's only 1.2 milligrams per liter per minute, and for 3 log, 1.43 per milligram per liter. So if you notice that it will be, here you can talk about 104 times stronger with respect to inactivation of any bacteria. You'll also notice that the activation or inactivation of the bacteria is also related to the pH. And for free chlorine, we put it as the optimum pH of 7. And for chloramine, which exists only in the pH 6 to 9, and for chlorine dioxide and ozone, the pH is 6 to 9. In this slide, we'll be discussing the use of organic biocides and inorganic biocides or oxidative biocides, and whether or not they can be used together. First of all, the non-oxidative biocides, which are called metabolic biocides, permeate into the bacterial cell and interfere with the metabolism of bacteria. The interference may just be one of the intermediate reactions that is necessary for a major biological function of the bacteria, which interference prevents the bacteria from growing further or kill them. This means they are like enzymes, coenzymes, destructors, or simply inhibitors of some vital reactions. The action is therefore time-related, the time for penetration, interference, and finally starving the bacteria to death. Ozone, on the other hand, as soon as it is applied, besides the electrovoltage destruction of the cell, will react the double, triple bonds and other groups of the bacteria cell and immediately destroy the cell function. It also immediately destruct the membranes, release the cell contents into the media, water media, and flocculate it. So it becomes totally inactivated. There is a question now whether or not you can use ozone and a biocide, organic biocide, together to increase the effect of the biocides. Unfortunately, it cannot be done. Wherever you use ozone as a biocide, you cannot use organic biocides simply because ozone attacks the organics. Not only the effectiveness of the organic biocide is destroyed or diminished, the ozone is also used up in breaking up the organics of the biocide, and therefore there will be less ozone to react with the bacteria. Therefore, we cannot use any organic material when we use ozone for a biocide. We did explain to you in some of the earlier slides that the smells are basically conjugated double bonds. Some of them are complex organic compounds which also have got double bonds. The halitosis is actually the odor that comes out of a person's mouth when he has very high level of bacterial action. And they have analyzed the gases of the halitosis and found that they are basically sulfur hydride groups, that is carbon, hydrogen, and sulfide. Now, the other organic aromatic compounds which produce smells also have got very high vapor pressures that will emit smell particular to the structure of the organic compound. You will note the typical almond smell of benzaldehyde, the vanilla smell of vanillin, the ethyl benzene and toluene have got slightly sweet odor, and ethyl hexanol has got a floral smell, and 2-ethyl hexanol, ethyl benzene, etc. will have a specific smell. Nicotine, which also has got some smell, the structure of nicotine is given in this figure, which has got hydrogen-nitrogen groups. Nicotine does not have much of a smell, but it can be destroyed by ozone. Odors are small volatile hydrocarbons that affect the olfactory senses. All of them have got double bonds, conjugated double bonds, nitrogen or sulfur linkages, which are all broken by ozone. So all you need is a trace of ozone that can remove the smell. In order to remove the smell, all you have to do is break one or two of the double bonds or triple bonds, and the characteristic of the smell completely changes. This session 9B. Thank you for the patience to listen to my presentation. If this is your first attendance, please refer to session 1 and 2, which gives the full course details, and sessions 3 to 9 that has been uploaded. The next presentation of session 10 will be on structure of virus and cysts. Please press the like and subscribe button so that you will be notified the upload of further presentations. Thank you and have a good day.